This is Free Range Digital Design Foundation Modeling, Chapter 26, and so this chapter we will be looking at counters. We've been dealing with counters in the previous chapter, but they were counters that were designed as state machines, so a low-level state machine design used for a counter. That's not what we're going to do. In this chapter, we are going to bump it up to a higher level. Counter becomes essentially a foundation module. Counters are a type of register. This is your counter here. It's a Venn diagram, shows the counter is a type of register, which means it has memory, the main feature of a counter. So the issue is it's kind of a register with features. Here, all sorts of counters out here. We will primarily be using binary counters in this chapter, and there's also, like I said, you can see all sorts of different types of counters out there, and we'll be talking about some of those, but not too many of those. Okay, and also the next chapter is going to be another type of register, which is shift registers. Counters are, once again, registers with features. They typically are a sequential circuit. They're synchronous also. Most of the changes in a counter are synchronized with the active clock edge. Last chapter we designed counters using state machines. In this chapter we're not going to do that. So the issue is that if you have a simple count like this is like a normal looking count, use a counter. If you need some type of specialty counter, like this strange count here, typically you're not going to get it with this high level counter object. You're going to have to use a state machine design, as we did in the last chapter. So many types of counters out there. Primarily we'll be using binary, and once again, another common counter you see out there is a decade counter. Essentially it counts in binary, counts faking out a decimal, so it means it counts 0 through 9, then it magically resets to 0. So binary counters, like a 4-bit binary counter, will count from 0 to some 2 to the n minus 1 value. So if it was a 4-bit counter, 2 to the n minus 1 is 15, it would count 0 through 15 and start over, and we'll see examples of that. When we start working with counters, there's all sorts of lingo, vernacular associated with counters. You need to know that vernacular to be able to talk about counter. We've seen the count sequence. So the count sequence is that sequence of numbers that the counter outputs. Typically, as we'll see, it outputs it on some active clock edge. What we want to start working with is n-bit counters. Typically n-bit binary counters, what we'll be working with in this chapter. So that means these counters count from 0 to the n minus 1, some value, and you put in the value for n. Typically counters, they count up, they count down, they count up and down, of course not at the same time. These are the typical counters that we'll be working with. So when you're counting up, you're incrementing. When you're counting down, you're decrementing. And when you're not counting, which means the active clock edge comes around and you don't change the count, it's considered a hold. Counters naturally underflow and naturally overflow. You don't have to make any special design on these, and essentially it's a notion of circular. So for example, a 2-bit counter would count in this sequence. But if it's an up counter, it's counting in this direction. It hits its terminal count right here, and it automatically goes back to 0. I can also count in this direction, which is a decrement. We'll say a down count. This is a down counter. Counts in this direction. Let's get that a little bit neater. E-O-W-N. So it's actually decrementing, counting the other direction. Once again, once it hits 0, the next count is going to be 1. So that's the circularness of these. It's considered, it overflows in the up direction, it underflows in the down direction. Typically these counters are cascadable, which means you can take 2 n-bit counters and very easily make a 2 n-bit counter. When we're working with HDLs, it's no big deal to design just a bigger counter, a wider counter. When you're working with discrete hardware, typically the cascadability is really a plus. Lastly here, typically these counters are registers, and they often have a parallel load, which means as well as counting, it takes advantage of the fact that they're a register, and you can load any value you want into that register and have it count from that spot. This is our foundation module for a counter. What we're going to see here is we got data coming in, which is the data that we're going to latch into this register, and that appears on the output. In addition to that, we have control signals such as a clear. A clear is just what it sounds like. It's typically asynchronous. Typically all the other control inputs are synchronous, such as a load. We got an up, we might have a down. Oftentimes we reuse the up signal such that when up is asserted it counts up, otherwise up is not asserted, it counts down. Also, these have hold inputs, but once again, once we're designing this, for example, we can say when up is asserted, counts up. When up is not asserted, it holds. So we have the flexibility to do pretty much anything we want in that. Another issue here is these counters typically have a status output, which is ripple carry out. What that means is it's just a signal that indicates when the counter has reached its terminal value. Now the issue with its terminal value is that it's dependent upon the count direction. So if it's counting up, the terminal value, the maximum count, is 2 to the n minus 1, and that's when the RCO would turn on. If it's counting down, terminal value is 0 because that's the least value. In that case, the RCO would turn on at 0 when it's counting down. Most important to look at here is, here's a state machine. These control signals are going to connect there, and these status signals are going to go there, and that's how I'm going to be able to control these counters to do fun and amazing things. This is a timing diagram associated with this counter up here. When I draw this counter, I have to say some extra stuff to it. So essentially up allows it to count up when it's asserted, or it says it decrements when not asserted. So up is actually both up and down, so this is necessarily an up-down counter. So that means RCOs is kicking out its terminal count when it's counting up and down, and I think you'll see this in this problem. Load signal typically is just what it is. It's a register, so this loads the register. Hold means it holds. So we got a bunch of inputs here. I have to actually specify the precedence of these. So load has precedence over hold and up. Hold has precedence over up. Let's do this problem. This problem's mostly done. I have all the control signals in there. What I need to do is fill in the data out and the RCO. And I think I will leave the RCO till last. And what I'm going to do here is work with just the data out. At this point right here, we see it's loading. So the value it's loading into the counter is this value here. So it's 110. At this point, the load turns off, and I see the up is asserted, and I see the hold is both up and hold are asserted. So I got to figure out what has precedence. Load has precedence over hold, and up, it's hold has precedence over up. So in this case, because it has hold has precedence of up, it does not count. It's actually holding. So no change in the data out. So next clock edge here, we have holds turned off, loads turned off, and we got an up signal, so it's going to count up. Next clock signal, what do we have? We have a holds off, up's off. Up is on, I mean load is off, so it's not going to load. It's going to count up, and the next count is going to be 0, 0, 0. It's circular, it goes around from its maximum count to its minimum count. Here we have an up, which is count up. Here we have a up not. Everything else is turned off, so it's going to actually decrement here, go back down to 0. Right here, but still counting down. And here we have a load turned on. Load has precedence over everything. This is the load that causes it to load, and that's going to load this value into the register, which is the same as this value, so that's going to be 0, 1, 1. So there's the data line. The next thing we're interested in is RCO. The two values we're interested in is 111 and 000. So if it's counting up and I see a 111, which is right here, that RCO is going to turn on. Here it is, it's still counting up, but it's at 0, so skip that one. Here's 0. This is just the terminal value in the down direction, so RCO turns on once again, and I don't see any 000s or 111s again. So these are the two locations that cause the RCO to turn on. We can actually put an arrow there to make that happy. and it's also a function of the down, so we can put a little dot there. So when this RCO is not on, it's off. Notice that this signal is a function, essentially a function of state. So you're never going to see the RCO change in the middle of a count. Oh, okay. And here's the when we're using counters, we have the ability to take that foundation module and use whatever inputs and outputs we want on it. For example, in this diagram here, we don't need an output. What we need is RCO, and this is fine. Okay, so this is a good drawing. It's obviously counting up. It's assumed that the up is synchronous. We all know what an RCO is. It's all going in one direction. So this is a valid circuit. This circuit here is also valid. It's an n-bit counter, and we don't really need to say anything about it. So this one here doesn't have an RCO. Let's assume that it's not. But it's a question of how these holds and ups work together. It's understood that hold, when it's asserted, it holds, and when it's not asserted, it can count up. But the question is, on this circuit, what does the up do when it's asserted and not asserted? You need to leave a note on this one, so I'll put a question mark on that one. This circuit has the same problem. It has data in, data out, no RCO. Load, it's pretty obvious what the load does. It loads when it's asserted, but once again, it's not clear what has precedence, the up or the load. Clear what the up does in its asserted and non-asserted state. You gotta state that in your diagram. So here's a clear, and it counts up. So this is a question mark, what the up does when it's not asserted. Also, generally speaking, I need to put asynchronous or not. Typically the clears are asynchronous on these counters, but you need to state it in the diagram. Okay, so once again, this is a big question mark because I'm not sure what up does when it's not asserted. Same issue here. Yeah, all of these have issues. Essentially what you'll see is when we do these problems, I need to put notes in them. So this is another case here where it's pretty obviously an up-down counter, but the question is, what happens when both up and down are asserted at the same time? Once again, you need to leave a note in your black box diagram, exactly how that works. This is another example of a counter, a timing diagram, so we'll go ahead and do that. And so what it says here is the reset here is negative logic. So this counter initially, we're going to put these bars in here to make sure we get it right. Because of this reset, we know this counter starts at 0. At this point, we're not loading, we're not resetting, but I got the up asserted. It does count up. At this point, I got a load asserted, which means it loads this value right here. This is going to cause that to load, which is loads turned off. It's going to count up 0x35. Looking good. Next clock cycle, the up turned off. Looks like a hold here. We're gonna put that in there soon. Okay, so that's valid. This clock cycle counts up right here, and so this clock cycle is, once again, we need to pull that out, is a hold, and also we'll hold it, and we see another hold there. Honestly, this should have been stated in the problem. If it's not, I'm just going to put a note in the problem solution. This is a problem where I need to count in this sequence. So what I have here is two issues. I got to count in this sequence, and it has an extra output that indicates when it's greater than 11. So this circuit's going to look like this. It has it's clocked. It's synchronous. It's going to have a count output, which I have to declare that. Certainly that's 4 bits will get that for me. And lastly, I have an LED on this. So there it is. But what I need to do, it looks like a counter. It's a really nice count sequence. It's always counting up, but for some reason it's loading this funny value here. It's starting at 6 rather than 0. This is really straightforward design, and so we'll do that. We'll pull our standard counter, 4 bits. There's my count. LED, we'll worry about the LED in a minute. There's the synchronous part. I got a data coming in on this. what I'm going to do here is make that data, it's 4 bits, I'm going to make it 6, 0, 1, 1, 0. That's on my data input. This has a load signal and it has an up. It's always counting up, so I'm going to tie that to always counting up. But the question is load signal. When it hits 15, I want this thing to load a 6 on the next clock cycle, and the trick for these is to connect the RCO to the load. Now, so when that RCO turns on, it'll turn on after the clock edge, and then the next clock edge, it will cause this counter to load. So when it hits 15, the RCO turns on, which is too late for the current clock cycle. Next clock cycle, it loads 6. I got one more thing here. I got to worry about that LED. Counter output is greater than 11. So greater than 11 is this. So every number that's greater than 11 has these 2 MSBs set. And so I'm going to put that in there as an AND gate. And I'm going to put a note in here. It says 2 MSBs. That looks good. I'll check this out. And this load here, I have to say, and I'm almost done. I have to state how this circuit is controlled. This is a control input, and this is a control input. What are they connected to? They're essentially connected to internal signals. So this is internal control. Here's an associated timing diagram. You can see that when it goes to 15, it causes the RCO to turn on, and when the RCO turns on, it's technically after this clock edge, but that RCO is asserted at the next clock edge, which means it's going to cause 6 to be loaded into the output of the counter, which is where this comes from. The other issue here is when you see this LED turn on, it's when the count is greater than 11. Once it goes back to 6, the LED turns off. One more problem here, and this is very much like the previous problem. Inputs 1 or 2 counts based on where their buttons pressed. It looks kind of really nice that it ends at 15, which is, we know that's the greatest number in a 4-bit counter, so that's kind of nice. And so let's go ahead and do this. I still have a 4-bit count. I have a special LED that we'll worry about in a minute. I think I'll give it a different name. And I have a clock. At this point, I know I can use a counter. Essentially, it's loading either a 3 or 6 into this thing based on a button press. So it's choosing 1 or 2 things. So I know this design is going to have a counter. I know what's going to decide that is essentially a button that's going to control the mux. And so the other thing I'm going to have in here is a counter that controls the main count of this thing. This is the data input, and this is our data output. This is 4-bit. We'll worry about that LED in a second. There's my clock. There's my up signal, it's always counting up, and then I have a load signal. So the issue is the same as last time. When that RCO turns on, I am going to load a new value into the counter. What value it is either 3 or 6. So we'll say button pressed, it goes 3, 1, 0. Not super clear in the description, but this is good enough. And I think I'm done with this thing. We need to make it complete. Looks good. No, so I have to do a couple things. We need to say how this is controlled. So this thing has 2 forms of control. This is a control input on the mux, which is controlled by an external signal, which is the button. Here's control signals on the counter. Those are internal. So this has control. And that's it. Okay, for this problem, we need to actually finish it up. We forgot the LED output on it. And so what we need is this counter has an LED output that indicates when the count is less than 8. So less than 8 means the most significant bit is 0. So what we're going to do here is take that MSB, invert it, and call it the LED. So that means it's less. If the MSB is a 1, that means it's 8 or greater. That 1 becomes a 0. when that MSB is 0, it must be 0. The number on the count output must be 0 through 7. And so this is what we need to finish this circuit off with.